Так, и на сегодня у нас последний доклад.
And this is our last presentation for today. Heikki Linnakangas will speak about user-defined data types in PostgreSQL.
There, that's better. So my name is Heikki Linnakangas. I work for VMware nowadays. Worked for Pivotal, which was then bought by VMware at the end of last month. So now I'm a VMware employee. So on my day-to-day work, I spend a lot of my time working on Greenplum, which is a MPP fork of Postgres. But today I'm going to talk about writing a user-defined data type in Postgres, which is applies completely to pure open source Postgres. So what is a data type anyway? A data type encapsulates the semantics and rules of what it means to have a piece of data. In Postgres, a data type usually has a text, or it always has a text representation. For an integer, you would have digits from 1 to 10. For date timestamps, you would have different representations. For strings, you just have the string. And the text representation is what you usually see. If you run a query, you get the text representation back, and also the application usually uses the text representation. So Postgres has many different kinds of data types. There's a whole bunch of built-in data types like integers, text, numerics, and then there's more complicated data types that are still built in like JSON, JSONB, point. There's also a bunch of extensions. PostGIS is a big one. There's also config modules in the Postgres itself. And there's, for example, there's a data type for storing ISBN numbers for books. And there's plenty of other data types out there on GitHub to do various tricks and things. And then you can also define your own data types using domains, which is just like any other data type, except that you can have like additional constraints on it. And there's also arrays, so whenever you have a type, you can always have also have an array type on top of that. There's ranges, so you can have ranges of integers that you can check if they overlap and so forth. And one very handy thing is the enum data type. So if you want to have if you have a column that can have like 5 different values, you can create an enum data type and deal with that. But those are not what I'm going to talk about today. I'd actually recommend using those things if you can. But what I'm going to talk about today is writing a new, what we call a base type from scratch in C. So this presentation is it's roughly divided into 2 parts. First of all, I'm going to walk through how to create your own data type, how to add some basic functions and operators to work with the data type, and do some basic B-tree indexing support. And then I'm going to talk a little bit more about GIN indexes, GIST indexes, and kind of more advanced index types and how you would do those with your own custom data type. When you create a new base type in Postgres, Postgres itself always deals with the Postgres itself internally really only deals with 2 kinds of data types. There's fixed length data types, which are, for example, 32-bit integers or 64-bit integers, and you pass them around by value. And then there are variable length data types, which is typically strings of text or JSON, or actually numeric is also a variable length data type, and many others. Where you have a small 1-byte or 4-byte header indicating the size, and then you have a bunch of data. But Postgres itself, as the core system, doesn't really know what's in the data type. All of the meaning comes from the functions and operators that you create on top of it. So all that the Postgres can do with the data is just copy it around, store it to disk, and pull it back from disk, and pass it to functions. Everything else is up to you as the data type author to define what these operations mean. So in this presentation, I'm going to walk through creating a data type for storing colors. So I'm going to store the colors as a 24-bit RGB value, red, green, blue. For convenience, I'm going to store them in a 32-bit integer, because then we can borrow a lot of the existing functions that deal with integers within Postgres. But if you actually cared a lot about how much space these take, then you might want to define it as a different length so that it takes less space on disk. So you can think of a color as a 24-bit RGB value. You have the red and the green and the blue components in the hex value, and that's the representation we're going to accept from the user. So let's get started. So the first thing you need, if you're going to write your own data type, is what we call the input and output functions. The input function takes a piece of text, a string, and it converts it into the internal representation, which in this case is the 32-bit integer. And the output function is the reverse of that. It takes the internal representation and turns it back into text. So when you do select star from a table, Postgres will call the output function for each of the value to convert it to text, so that you can see it in the result. So in our example, we're going to write this in C. That's the only option for the input and output functions. You have to write them in C. And for performance reasons, you would want to do that anyway, but there is really no choice. We're gonna accept strings like this with the hash in front and then the numerical values of the red, green, and blue components. So this is what the input function will look like. You get as an argument, you get a string, and then we have some C code to check what it looks like. It has to begin with a hash, and then it has to have hex digits. If it doesn't, then you throw an error. And then you use the standard libc functions to convert it to an integer. That's pretty simple. The output function is also very simple. It takes as an argument, like an integer, and then it just prints it into a text, and then it returns that thing. I'm not going to go through the details of these, but I recommend if you're actually writing your own data type, you pick either these examples from my presentation, or just pick any of the built-in data types and copy-paste this stuff from them. So we now have the input and output functions. There's one more thing we need to do. We have to tell Postgres about them. Otherwise, they're just C functions. So you have to tell Postgres that, OK, there is this function called color in and color out. And with the create function command, you can make them callable from SQL code. And finally, we create the type. You tell it what the input and output functions, and I'm going to use this shorthand like here, which tells that it's going to copy a lot of stuff from the integer data type. I think I'm going to talk more about that later. So this is the bare minimum you have to do to create a new base type. And now you have a type. You can now create a table using this type. You can insert values into it, and you can select stuff back from it. That's already pretty awesome. Now you have your own data type to store colors. This is the full help output for the create type command. As you can see, there's a lot more you can do. We only use the input and output functions for now, and I used the like option to tell that all of these other parameters were copied directly from the integer data type. But for example, you can see that there's binary receive and send functions, which are kind of like the string functions, but for binary format. There's type mod in, type mod out. If you have a data type that takes a type mod, for example, car10 or car20, or numeric with a length, that length is what we call the type mod. So if you want to define a function that takes a type mod like that, then you would have to define these functions. There's a lot more stuff you can do. For example, you can specify your own analyze function so that when you do analyze on a table, Postgres, the analyze function defines what kind of statistics you want to be collected for that function, for that data type. But I think this will do for now. Let's move on to operators. So with the data type we created, you can't actually do very much yet. So if you'll try to run a query like this, you'll get an error saying operator doesn't exist, color equal unknown. Postgres doesn't know what equality means for this data type yet. So what we need to do next is to create the equality operator. In this case, since we can borrow the integer equality operator because we're using the same on-disk representation as a 32-bit integer. So we only need to do this create function command. It says, OK, so we have a function called color equality. It takes 2 color arguments, and it returns true or false to say whether it was equal or not. So that's very simple to implement. Once you have the function, then next you create the operator saying, OK, there is this equality operator, and this is the function to back it up. So this works now. You can now do select from the table and use the equality operator. So when you run this query, Postgres will call the input function for this constant that you gave. Then it will scan the table, and for every row, it will call the equality function that we defined and returns those rows where your function returned true. So that's pretty cool. Next, I'm going to define a few more functions, just because typically you want to do some stuff with your data types. So I'm not going to show or go through the details of the C functions, but let's define 3 functions to extract the red and the green and the blue components, and then you can use them in queries as well, and you can see how that works. Next thing I'm going to do, I'm going to create this function called luminance. So when I started to write this presentation, I did some research, which means I Googled for 5 minutes about colors. And I found this concept called luminance, or relative luminance. It turns out that the human eye is more sensitive to green color to the other colors. So if you have bright green, it looks a lot more bright than, for example, blue color. So I'm going to create a function that has these factors for luminance, which basically means how bright does the color appear to be to a human eye. By the way, if anyone has any questions, feel free to interrupt me. Otherwise, I'm just going to run through these examples. So I'm going to define this function for luminance, which returns a numeric between 0 and 1, 1 being completely white and 0 being black. And you can see that you can use that function in your queries as well. And of course, you could create like as many functions like this as you need. So the summary so far, we have created the user-defined data type, base type with input and output functions. We have the equality operator and some functions to deal with that. Ordering. So the next thing you might want to try to do is to do order by. And if you try to do that, you will get another error which says, couldn't identify an ordering operator for data type color. Of course, we haven't told this Postgres yet, how do you order? What does sorting mean for colors? And so with sorting, you have, in order to define sorting, you have to create 5 operators. I think it's pretty clear to see where this is going. So you have to have less than equal, equality, which we already did, greater than or equal and greater than operator. And you have to define all of these operators to do sorting. And this is the real reason why I wanted to create the luminance function, because I'm going to use that luminance function for the ordering, so that you can do order by color data type, and it will order them by the luminance of the color. So let's start implementing these things. These functions you can actually write in SQL, because we already defined the luminance function. So I'm going to define the less than function just by, calling the luminance function for both arguments and comparing that. pretty straightforward. Same thing for all of the other functions that we were missing, those less than and equal, greater than. And once you have done that, we also need to create the operators on top of the functions. So when you do color less than the other color, it will call this function to return true or false. One more thing we're going to need. In order to do sorting, Postgres also needs what we call a support function, which is a comparison function which compares two color values and just returns 1, 0, -1, depending on which one is greater, which one is bigger. Obviously, Postgres could do this just by calling the less than or greater than functions that we had to define anyway, but for performance reasons, it expects that you create one of these comparison functions to do it for you. We're not too worried about performance right now, so I'm just going to implement it in SQL by calling the less than operator. So now we're ready to do ordering. What we have to do with these operators next is to tie them together. If you just create the operators, Postgres doesn't know that they're related to each other because just because an operator is called the less than. Yes? Question?
In the previous slide, it's
Sure.
На этом слайде вот есть вариант для нуля, для единички и для минус единички.
The slide represents values for 0, 1, and -1. What if two colors have the same luminance? How is it resolved here?
It's probability that two different colors will have the same luminance. And
Yes.
This function doesn't cover this chance.
Good point. Yes, I think you just found a bug in my function. Yeah, it's true that there could be two functions that are not equal, but they have the same luminance. Good point. I should fix that. Yes. So it's completely possible to create bogus functions, and who knows what will happen if you do that. So once you've created all of these functions, you have to tie them together. So Postgres has this concept of operator classes. The separate operator classes for different index types. So for sorting, we use the B-tree operator class. And by putting all of these operators in the same operator class, tells Postgres that they kind of work together. Otherwise, Postgres wouldn't know that, for example, less than and greater than have any relationship with each other, so you have to tell it that. So in this case, I'm going to create the luminance operator class, and I'm going to mark it as a default for the type color. You can have multiple operator classes for the same data type, so we could define another sorting operator class that uses something else than luminance. For example, you could create one that just compares the red component or the green component or whatever makes sense for your application. But in this case, we're going to go with the luminance. So once you've created that, you can do ordering. These colors here, they're not from Postgres. Postgres doesn't do colors. I just drew them here for illustration purposes. But you can see that when you do select star from the table and order by the color data type, it will return the green one is first. Well, the white one is the very first, but after that you get the green ones because the human eye is more sensitive to green color. And then at the bottom you have black. And as you can see, there are no equal. None of these are equal, so this bug doesn't arise. But of course, if you had more rows, then that bug might actually cause incorrect results. But Postgres is happy with that. If you have a bug in your functions, it just means that you have garbage results, basically. But Postgres itself is going to be totally happy with that. So now you can do ordering that we have defined this B-tree operator class for that. Next thing I'm going to do, I'm going to create an index. I mentioned that what we actually just created here is called the B3 operator class, and of course the B3 refers to the B3 index. But in Postgres, the B3 operator class has a bit of a special status because it's also used for ordering. So when you do order by, and it will use the default B3 operator class for your data type. And any time that Postgres needs to do sorting, it will use the B3 operators for. So for example, if you have a join and Postgres wants to do a merge join between two tables, merge join requires sorting both inputs, and it will use your operator class to do the sorting for join purposes as well. Or if you do group by, it will use this. If it decides to do a sorted grouping operator, it will use your operator class to do that grouping. But you can also use it to create an actual B3 index on this thing. So now we can create an index, and when you run the create index command, you run the same query as before, you can see that you get an index scan based on your operator class, the things you defined. Again, if you have a buggy implementation like I did, then it's kind of all bets are off what results you get when you actually try to use it. But Postgres internally will be perfectly happy with that, so it's not going to cause crashes or anything like that. It just means that you might get incorrect results, which is unfortunate. But of course, you shouldn't make mistakes. So, summary so far. We created the type, input and output functions. We created a bunch of other functions to work with this. We also created more operators and the B3 operator class. So this is pretty basic stuff. And as I mentioned, Postgres uses the B3 operator class also for grouping and ordering, for merge joins and stuff. So even if you don't really need to create an index, you probably still want to create some kind of a B3 operator class just for performance purposes. And in fact, the hash operator class is similar. As you might know, Postgres has an hash index type, hash index access method. Almost no one uses that, but in any case, whenever you create a user-defined data type, you should always create a hash operator class too, because Postgres will use that hash operator class also for hash aggregates and hash joins, even if you don't want to create an actual hash index. So hash operator class is another kind of a special case with the B3 operator class. Creating the hash operator class is a little bit simpler. For hash, you only have one operator, which is equality, and the support function for hash would be your hash function, so you get to write your own hash function. I didn't bother to do that in this example, but for any real data type, you probably would, because then you can do hash joins and hash aggregates. Of course, you can create your own casts. So if you wanted to be able to cast between colors and integers or something, you can use the create cast command. You could create cross data type operators. So if you want to directly compare colors and integers, you could create equality between the different data types. I mentioned earlier that you could create an analyze function. So if you want for the planner to decide what's the selectivity, how many rows are you going to get for a query, you could define your own analyze function to collect statistics for your data type and whatever that means for your data type. What you get by default is the list of most common values, which is already very useful. And if you define the B3 operator class, then Postgres by default will collect a histogram of ranges of values and how many of these are there, another range, how many of these values are there, which is usually pretty good. But for special purposes, you might want to overwrite that. So, if you're going to do all this, I just showed you the C code, and I showed you the SQL commands, the DDL commands to create the functions. But how do you actually put this thing together? What you would typically do is to you would want to package this thing as an extension, so you have everything in one package that you just have to install. For an extension, you put your C code in a .c file, and you have a make file that you should copy-paste from one of the existing ones, so you get it right. And then you have a control file that specifies the name of the extension and some other metadata. And finally, you have the .sql file, which contains all of these create function, create operator, create type, all of these SQL commands I showed earlier. Then when you put them all together, you have an extension. As you may notice, I did this presentation for the first time back in 2013. I actually I kept it up to date over the years, but I just went back and tried to compile all of these examples, and they still worked against Postgres 12. So these APIs, these functions have been really stable, at least since 2013, apparently, because everything compiled without any changes. So this stuff is pretty stable. So let's talk a little bit about more advanced stuff. So in the previous examples, I did order by luminance, which is nice. But what about finding the color that is closest to a given color? Like if you go to a car dealership with a piece of paper that has a specific color, you would ask them, what cars do you have that are close to this color? Or maybe if you run a paint factory, what is the closest paint you have to this specific color? Well, we have to define what does it mean to be the closest color. And I'm going to use a simple distance function. So I'm kind of imagining that the color is a point in a three-dimensional space, so you can compute the distance between two colors with this formula. So here is the same formula implemented in SQL. So I'm creating a distance function, color diff, and then I'm going to create an operator using that function. This looks very similar to the previous stuff, but I'm just giving it a different name. So now you can use that. You can do order by this thing. And you can see that if you give it as input the color green, you will get green. Well, that's the first one. And then you have a lone green and, well, some other colors. And blue and red are definitely not green. So they're in the bottom. So that's pretty cool. That was very simple. Unfortunately, if you just do that, there's no indexing support for that yet. So maybe you can see where this is going. So at the moment, you would get a sequential scan on that, which could be really slow if you have a billion rows in your table or something ridiculous. That could become slow. So can we build an index for that query? And it turns that, yes, we can. Postgres has several advanced index types. We talked about B-tree already. I mentioned hash. Those are kind of special because Postgres uses them for sorting and hashing in general. But then there's these other data index types, gist, gin, spgist. Oh, there's a typo. It should be spgist, and brin, which all have slightly different properties. The gin index is typically used for full-text search and arrays. Gin indexes work so that you extract some kind of elements from your piece of data. Like for full-text search, you would split the text into words, and then you index each of the words separately. For arrays, you would index all of the array elements separately. And what you can then do is you can do queries like, give me all the records that contain this word, or give me all the arrays that contain this element. And there's also plenty of other examples of where this might be useful. Now, for the color data type and this problem, it's useless, so I'm going to skip over this one. But it's good to know that it's out there if you have that kind of a data type. For JSON, it could be useful to extract the key and value elements or something like that. But for the color data type, not really useful. What we are going to use is the gist index. The gist stands for, I don't actually know it. The G stands for general, and I think S stands for structure, and T for tree, but I'm not sure exactly what the acronym is. But the gist index is a general tree structure. It's very flexible. And basically what you have to do is to write these support functions to define how do you put the stuff in your tree. It's typically used for geographical data. You can build an R tree data structure using it. It can also be used for full text search and trigrams. But the R tree is the very typical application, so I'm going to talk a little bit about that. So if you remember the B-tree stuff, what we did for B-tree, we had these 5 operators and 1 support function, which was the comparison function. All of these other data indexes are similar. You have operators and support functions. So for the gist, you have 8 support functions instead of 1. And these Postgres will call these support functions to build the index. So you have the consistent function. When you're searching, you go down the tree. It calls the consistent function to decide which parts of the tree you need to go down into. And you have a union function, which is used when you insert new values, compress, decompress, they're not important. There's a penalty function that's used when inserting to decide where to put your value and so forth. And so using these functions, when you define these functions for your data type, you can build the search tree. So for example, for the R tree, the way an R tree works is that if you're indexing points, the upper layers of the tree will contain bounding boxes, and the lower levels of the tree will contain smaller bounding boxes, and the smaller bounding boxes, and so forth, until you get to the leaf level where you have the individual points. To create like an R tree using gist, you would have a consistent function which compares your point with the bounding box and says true or false, depending on whether it's inside the box or not. And the union function would make the box larger so that the point fits into it. And yeah, I think I have the examples here. And the penalty function would look at the distance, how far is this point from the bounding box, and so forth. And in fact, there is an R tree implementation in Postgres core itself for the point data type. So if you wanted to do this, you would look at the Postgres source tree and find these functions for the R tree implementation and use those. That's also how PostGIS indexes work. They also use an R tree, kind of in a similar way. So how is this useful for our color example? Well, if we think about colors as points in a 3D space, in a 3-dimensional space, we can use an R tree in the same way. So just instead of having a bounding box, you have a bounding 3-dimensional cube at every level. So I didn't actually go through and implement this, but there actually is a 3-dimensional R tree implementation in Postgres source tree. In contrib, there is a cube contrib module that pretty much does this, so you could copy-paste that implementation very easily. Well, or you could just use the cube data type itself to store your colors, which would be perhaps simpler. But the point is that you could do this if you wanted to. We're getting to the end of the presentation, but the point with all of this is that when you create your own data type, you get to define what all of these things mean, and when you create for the indexing stuff, you get to define what does the tree looks like with these support functions. You define all the operations and meanings for your data type. It's worth noting that I didn't say anything at all about while locking. I didn't talk about that backup and restore at all, or locking, or concurrency isolation. And the reason for that is that Postgres will just take care of all of that for you. You don't need to worry about that stuff, because that's all built into the actual index implementations that calls your functions, but your functions, don't need to worry about this stuff. And I think that's the real power, and kind of the interesting part of this presentation is probably the stuff you don't need to do, which is all of that stuff listed there. So if you're more interested in this stuff, you should look at the source code. The Postgres source code is very readable if you just find the function you're interested in. There's plenty of examples in the documentation. There's plenty of stuff on GitHub if you want. Also, this stuff is available on GitHub if you want to look at the actual code involved in this presentation. Questions? Yes.
Thank you, Heikki.
Thank you. When you define user function in the third slide, maybe create type,
Yes.
and any function in, out, and as I remember,
Let's go back.
function send and receive maybe was be mandatory. Receive and send. Can you show for what this function?
Right, so what is the send and receive for? Yeah, I kind of skipped over those. If you use pgdump and you specify the binary format, I don't remember what the option is called, but if you use pgdump in the binary format, it will call the receive and send functions instead of the in and output functions. It does the same thing, and in fact, or it's very similar, but it's implied that your send and receive functions can be in binary, so it doesn't have to produce a string. It can produce just a blob of binary data. It doesn't have to be human readable, basically. But actually, many of the data types, like for the text data type, for example, it looks exactly the same as the input and output functions, and that is a common way to implement it if you don't care. Some clients also prefer to use the binary format. So on the wire, when the client connects for a specific query, it can say that it wants to use the binary output instead of the text output. Most clients or drivers, if you have a JDBC driver or whatever, they will do it for the data types they know. So they will usually use the binary input and output functions, the receive and the send functions for things like numbers and that kind of stuff, because then you usually avoid some overhead from converting the text and back from text. So it's really a performance thing. But if you don't define them, then you can't use the pgdump in binary format. So you probably want to have a dummy implementation there, even if you don't really care about the performance.
Еще вопросы?
How do you recommend to test the functions? How do you recommend to ensure that your functions works with the different versions of PG?
How to test with different versions? Gee, I don't know. You just install multiple versions of Postgres, I guess, and test. As you saw, I didn't test these functions very well because there was a bug. But I don't know. How do you test your application in general?
I mean that any soft you have written needs some kind of test coverage.
Yeah, I would highly recommend that you write tests for sure. It's always a good idea. In this case, I think you could use the Postgres' regression test stuff we have, which is you basically just write your own SQL file that runs these queries and check that you get the results that you expected. That's actually, data types are pretty simple to test because you can write queries and check that you get the right result.
Thank you.
Do what? Sorry?
As example. For testing, you can use PGRegress tool that incorporated into Postgres core.
Yeah, PGRegress. Is that PG_regress? Yes.
In create type, you mentioned that you would make it like integer.
Yes.
What do you get from this?
So when you specify like integers, that's a good question. You get the length. In this case, it was a 4-byte integer instead, and not a variable length. You get the passed by value. So within Postgres, there's actually two different. I mentioned that there's fixed length and variable length, but there's actually another dimension, which is it passed by value in your C code or passed by reference? So you get that. Alignment, some things we tend to align at 4-byte or 8-byte boundaries for performance reasons. At least those things. I'm not sure about these others. I think it's the internal, whether it's fixed length, alignment. At least those things. I don't think it applies to these other options.
You don't get those operations or the operator class.
Right. You don't. Yeah. You don't get any operations. It's just the internal representation you get.
Yes, thank you for this very useful presentation. Can you specify a little bit about all the parameters, just for a summary after like? Those I don't know.
You mean this?
Yeah.
So, yeah. Category. Category you would use, I'm not exactly sure how it works, but it's used, for example, for integers. Postgres has 2-byte integers, the 4-byte integers, and 8-byte integers. And then there's numeric, then there's floats. They're all in the same category because they're all kind of numeric values, just with different lengths. And so it affects. I think it affects the way casting works. And for example, if you define a function, but you then try to pass as an argument different kind of a data type, whether Postgres will do the conversion for you automatically or not. So the category is used for that. So if you have multiple data types that are like in the same, I don't know, family of data types, then you would put them in the same category. Preferred. I don't remember what that does. I think it's also related to casting somehow. Default value, you could specify a default. I think that's more for domains, maybe. Element and delimiter has to do with arrays. So I don't think you can actually specify them for regular data types. But if you're creating your own array type, which I'm not entirely sure why you would ever need to do that, you could specify, okay, what is the element type of this? So what you would say, if you wanted to create a new array type for arrays of integers, then you would say element is an integer. And in that case, the delimiter would be, it would affect the string representation. So when you say, when you have an array, you would have like the funny parentheses, and then value, comma, value, comma, value. If you wanted to do something else than a comma to separate them, then that would be the delimiter. Not something you would typically want to do, I think. Unless, I guess, the comma has a special meaning, you would want to avoid that. Collatable effects, it's really only for string data types. So if you have a string data type, where you want to care about collation, which means collation means how do strings compare in different languages. So depending on your locale, you might want to sort them differently. In that case, you would use the collatable true, but otherwise you wouldn't. Yeah, there's a lot of options there.
Так, еще вопросы есть?
Okay, other questions?
Thank you.